Hello, Debarati ma'am. Debarati, Debarati ma'am, can you hear me? Hi ma'am, good morning.
Hello.
Hello.
Should we get started?
Yes ma'am.
Should I admit all?
We can start ma'am.
Okay. All right. Can you please enable so that everyone can
Yes, I already did.
Okay. Thanks. Share my screen. Okay. Hello. Good morning, everyone. So my name is Debarati Chatterjee. I'm an associate professor at IUCAA. And so this is the second lecture in a series on compact stars for the IUCAA Introductory Summer School and Refresher course in Astronomy and Astrophysics. So you can unmute yourself, so you can put your hand up if you have a question. I will try to stop in between. Otherwise, of course, you can ask me questions at the end of your talk. There is also a Google form that was circulated with you, so you can put your questions there and I can upload the answers later in the workspace. So yesterday we talked about the what compact stars are, how they are formed, also a little bit about observations, what we can learn from multi-wavelength, multi-messenger observations of compact stars. And so today we are going to delve into the interior of a neutron star. So we are going into the realm of nuclear astrophysics and astroparticle physics today. And we'll try to see how the observations we talked about yesterday, they can help us understand the extremes of nuclear and particle physics. So yesterday we talked about I showed you this slide. Remember that white dwarfs are, this is what the interior structure looks like. So for white dwarfs, there is a hydrogen shell, a helium shell, and carbon and oxygen core. And for the neutron star, I told you that there are different layers. So today we are going to learn more about this, and also how to model the interior composition of these exotic objects. So, so remember that yesterday we talked about how these objects are stable. So what gives them stability? So basically, it's the fermions that constitute these objects. So for white dwarfs, it is electrons, and for the case of neutron stars, these are neutrons. And remember, I told you that these are fermions. So fermions are a class of objects, so objects which have half integral spin. And I also told you that they obey Pauli exclusion principle, which means that they are not allowed to crowd together. They can only occupy a single state, and therefore at zero temperature also they occupy a certain number of levels, as opposed to bosons, which all go to the ground state. So this level, the energy level up to which fermions fill up at zero temperature, this is called the Fermi energy. And also, you know that energy and momentum can be related in relativity. So we will learn what this tells us about the equation of state. So we'll come to this. So if we represent instead of energy, so here you see at the bottom there is a figure of probability as a function of energy with respect to Fermi energy. You see that it's like a step function. So it's 1 and then drops off to 0. Okay, so this can also be represented by a sphere in momentum space, where these are, so kx, ky, kz are the momenta in the three different directions, so the three coordinates. And so Fermi energy in this space will be represented by a filled sphere. So all the levels inside the sphere are filled and outside are 0. So the number of states at momentum k per unit volume is calculated as, so represented by dn. So this is d3k divided by 2 pi h cubed. And this comes from the, so you can imagine that, n is the number of particles per unit volume, or number density. So basically this is the volume of this shell of, so a shell in momentum space. And this is also written by 4 pi k square dk if you write it in terms of the spherical coordinates, integrating over the spherical coordinates. So I'm going to show you a little bit of the calculation in order to understand how this works. So once you have the number of states at momentum k per unit volume, so like I said, so dn is given by d3k by 2 pi h bar cubed. And then you can integrate over all the momenta from 0 up to Fermi energy, Fermi level. So the level up to which the sphere is filled. And so you get the number density. So you see that the number density and the Fermi momentum are related, as n is proportional to cubed of the Fermi momentum. Similarly, now if you want to find what are the number of, what is the energy density, so the energy per unit volume. So what you do is, now instead of, so now you write energy as, so you know in relativity you can write it as k square c square plus mn square c to the power 4 square root or to the power half, and then you integrate this over momentum space. So similarly, so this gives you the energy density. And so these are written in terms of some dimensionless quantities. Now, in the same way, you can write down the pressure. So now the pressure can be written as 1/3 of the volume times momentum. So you know that this is how you can write pressure. And again, integrating over momentum space, you can write it in terms of these x and u, which are dimensionless quantities. So, I mean, basically, this is the mathematical formulation of how to calculate energy density and pressure for a system of fermions. So this is a simple calculation. You can also try it out on yourself, by yourself. So this relation now between the pressure and energy density, this is a very important quantity in astrophysics. So, I mean, in general, for any like even ideal gas, it is the relation between pressure, volume, and temperature. And here, temperature is 0. So we are considering a cold neutron star. So the relation between pressure and density, or pressure and energy density, is called the equation of state. So if you calculate these integrals, now you can see from some simple math that if x, so x here was defined as this dimensionless quantity kf, so Fermi momenta divided by mc, which is the rest mass of the nucleon. So, so neutron is, for example, or electron. So you can do a simple calculation to see that if x is much less than 1, then P becomes proportional to this energy density to the power 5 by 3. And K and R is a constant. If on the other hand, you take another limit, so now Kf is much greater than M, then you have P is proportional to energy density to the power 4/3. So what are these two cases? So x much less than 1 and x much greater than 1 are actually two cases where the momenta are either much less than rest mass and much greater than rest mass, which means one is a non-relativistic equation of state and the other one is an ultra-relativistic equation of state. So in general, both of these can be written in a form P proportional to e to the power some index called a polytropic index, and this is said to be a polytropic equation of state. So what did we learn? So this is a summary slide of what I just said in numbers. So the summary is this. So fermions obey Fermi-Dirac statistics. So we'll know that according to Fermi-Dirac statistics, and this number density was such that it is related to cube of the Fermi momentum. The energy density, so this can be written in terms of these momenta, and so the pressure can also be calculated like we did. And also the energy per particle can be calculated. So this is nothing but the energy density divided by the number density. And so in general, what we found was the polytropic equation of state. The polytrop means that pressure is written as a power of the density, and this power is called the polytropic index. So in case of non-relativistic electrons or neutrons, whatever, non-relativistic fermions, this is related as rho to the power 5/3, and for ultra-relativistic electrons, this is rho to the power 4/3. So these can be represented if you plot this relation. So you can write, I mean, you see a cartoon here on the top. So pressure, energy density, this will give you a curve, and this is the representation of the equation of state, the simplest polytropic equation of state in the case of a fermion gas. So now let's see how well this describes the systems we are talking about. So electrons were white dwarfs were simple. White dwarfs were just composed of electrons. So in that case, what we do is now, if we want to calculate the structure, you know that the stable structure for white dwarfs is given by the balance of gravity and pressure. So in this case, this is how we can write down the equations of hydrostatic equilibrium in the case of a white dwarf. And what is this? So this is the relation between dp dr and the relation with rho, the density or energy density, and dm dr relation with rho. So where does it come from? So this is also a math that I'm not calculating here, but this is simple to understand. So dp dr is the change of pressure with respect to radius. So here, for example, in this cartoon, if you take a radius of r and then a shell of r plus dr, so a shell, consider that. So the change in pressure with change in radius is dp dr here. And this can be obtained from Newton's law. And dmdr is nothing but it comes from the relation between mass and volume. So now, if you solve this equation, you can do it like there are numerical techniques, numerically this is simpler to do, because analytically there are techniques to do this. But the basic idea is this: in order to find the mass and radius, what we do is we start from the stellar center. So the stellar center corresponds to R equal to 0, central energy, central pressure, and 0 mass. Then we integrate outwards using these relations and the relation between pressure and density, which is the equation of state. And then you see that dpdr is negative, which means the pressure will decrease towards the surface, and the point where it goes to 0 is the surface of the star. So you see here on the right, this is the relation between masses and radii. So mass on the x-axis and radii on the y-axis. So this is the mass-radius relation for a white dwarf. And this you can also try and calculate by yourself and see that it leads to this limit of 1.4 solar mass that Chandrasekhar had given us. So now it should be practically very easy to do the same thing for neutrons. So what are the differences? So for neutrons, if you do the same thing, neutrons are also fermions. You take a polytropic equation of state between pressure and density, and then you integrate outwards. So now there is a difference in the sense that white dwarfs, we used Newtonian calculation, because white dwarfs are not as relativistic they are not as compact as neutron stars. We can also add general relativistic correction here, but for neutron stars, this is absolutely essential. So this was first done by Tolman, Oppenheimer, and Volkoff. So it's called the TOV equation after them. So these are nothing but the same dpdr calculation, but there are general relativistic correction terms added to it. So if we do the same thing now, numerically we integrate outwards and calculate the mass radius. So you see the curve on the right. So this is what we obtain. Now there you see that there is a maximum mass, and this maximum mass actually comes from the fact that the change of pressure with change of energy density, this cannot increase infinitely. There is a limit because of dpde is actually speed of sound squared, and you know that speed of sound squared has to be less than the speed of light. So there is this constraint coming from relativity, which means that there is a certain maximum mass, and beyond this the mass starts to decrease. So this is the typical mass radius relation of a white dwarf, of a neutron star. Now, funnily, if you see the value corresponding to what we got for like free neutron gas, it's very low. So it's just 0.7 solar masses. Okay, so now let's try and think, what did we forget? So, okay, we assumed in the first place that there are only neutrons. Like I said, that this is not exactly the case. So neutrons in free space, they decay into protons and electrons and emitting neutrinos. Now, in finite nuclei, this decay is possible if the final states are not occupied. But inside the neutron star, you have infinite nuclear matter, and these protons electron levels are filled up, and when they are filled up, there is the reverse reaction also possible, which is this electron capture reaction that I talked about earlier for supernova explosions. So now there is a balance between these two equations, giving us a chemical equilibrium. So chemical equilibrium is represented by chemical potential. So this is nothing but the derivative of energy density to number density. So you can write mu n is equal to mu p plus mu e from these two reactions. So this is a balance of the beta decay and electron capture. Now, is that all? The other thing that we have to remember is that neutron stars in total, in general, have to be charge neutral. Any astrophysical system like this has to be charge neutral. Otherwise, Coulomb forces will rip it apart. Coulomb forces are much stronger. So if we take that into account, only protons and electrons are charged, so their numbers must be the same. So now let's put these constraints also in our calculation. So now when we redo the calculation, we see that the mass did not change much at all. I mean, it's understood because, like I said, it's primarily a neutron gas and there is a small fraction of protons and electrons. So again, the question is, what is missing here? So we can understand pretty well from this that neutron stars are not like white dwarfs. They are just not a simple neutron-free gas. So what is missing here is actually the key question here. So the nucleon-nucleon interaction. So now you see that neutron stars are perfect astrophysical laboratories for studying dense matter nuclear physics. So how can we model this nuclear interaction? So this is the most difficult part of the calculation of neutron star interior or structure, or whatever you like to say. So there are many different techniques. I will not go into the details because they are really much complicated and they are unsolved problems as of now. So the nucleon-nucleon interaction is modeled by two main techniques. So one is called a microscopic model, which means that in this case, these nucleon-nucleon interactions are calculated with the help of some underlying like vacuum physics, and then like these nucleon-nucleon interactions are so two body forces are taken into account, and then three body forces are added onto it, and so on, because we don't know how a large number of nucleons interact among themselves. So when we consider only two nucleons, how do they interact? So for example, you see this Feynman diagram on the right. So protons, neutrons, they are thought to interact via meson exchange. So this can be one of the pictures. So there are some models like Bruckner-Hartree-Fock models which do this. So they take into account this nucleon-nucleon interaction and then try to see how to implement this into the equation of state. There are also other models. There is another class of models. So this is simpler. So these are called phenomenological models. And from phenomenological, the word you understand that these have to do with experiments. So what is done is that these models have some effective density dependent interactions. And the parameters of this model are adjusted. These are free parameters and these are adjusted in such a way that they reproduce experimental observables, like what is measured in nuclear experiments or hypernuclear experiments. And again, these can be non-relativistic or even relativistic ones. So these are different classes of nucleon-nucleon interaction, how it is implemented into equations of state. Now, what do experiments tell us? Because here we talked about fitting them to experiments, right? So remember that when we are talking about experiments don't give us the whole picture. And why is that? So this is a diagram of the behavior of matter at different densities and temperatures. So nuclear experiments, they probe, so here the two axes are, so the x-axis is the baryon density or the density as a function of saturation density of matter or the nuclear density of matter. And the other one in the y-axis is temperature. So early universe is high temperature, low density. Okay, nuclear experiments that we conduct, so these are at 1 because, like I said, saturation density or N0 here is nothing but the density of nuclei. Now, there are other experiments, terrestrial experiments, like you must have heard of heavy ion collision experiments, accelerators like CERN, or so there are also GSI, so FAIR experiment is at GSI, NICA, and so on. So these experiments, actually what they do is, I will come to this as well, so these experiments collide heavy ions, right? So heavy ion collision experiments. So these probe matter, which is hot, high temperature, and dense. Now, so nuclei, you saw that these are cold and not dense, low density. Heavy ion collision experiments are intermediate density, intermediate temperature. Where are compact stars? Where are neutron stars in this figure? They are at the very bottom because they are zero temperature, and also they are at higher densities. So they start with nuclei, because at the surface, I will show you the structure again later. So the surface of neutron stars have nuclei, and as you go deeper and deeper, the density starts to increase. So 2 times, 4 times, up to 10 times that of what we get in nuclear experiments. So these are going along the x-axis. Another point is that all the experiments we talked about that we conduct on Earth, nuclear experiments, heavy ion experiments, these are all have the same number of neutrons, protons. But neutron stars, they are mainly composed of neutrons. So what do we have when you have such a neutron-rich structure? This is not very well known. Now, so keeping this in mind, that when we are fitting our parameters to some experimental observables, can we directly use them? No, right? Because we have these extrapolations to low temperature is okay, low temperature is fine, but when we go to higher densities and higher asymmetries, then we have to extrapolate to an unknown regime. So what information do we get from nuclear experiments that can help us to model neutron stars? So one information that comes to us is in the form of binding energy of nuclei. So nuclei, so for example, a nucleus with atomic number A and charge number Z, this is not only composed of n number of neutrons and Z number of protons, but also there is this binding energy. And if you have had a course of nuclear physics, you know that Bethe-Weizsäcker formula, so this expresses this binding energy. And this binding energy can be written as a volume term in the sense that the binding energy is proportional to the volume. But then there are also corrections coming from surface term, AS, there is a symmetry term because of asymmetry, there is a Coulomb term because of charge, pairing correction, shell correction, and so on. So it's basically like you can imagine a drop of liquid, it has a volume, and then you have to correct it because it has some finite size effects. So ideally, we would like to calculate the energies for infinite nuclear matter. So like neutron stars, we consider these are infinite nuclear matter. But then as soon as you put it inside a surface, there are all these surface effects that you have to remember and take into account. So this is what can be measured in nuclear experiments. So now, like I said, so nuclear experiments, so this binding energy or energy per particle can be written in as an expansion, as a Taylor expansion in terms of either isoscalar properties, which means these properties are blind to the number difference between neutrons, protons. And so these are like saturation energy. The second order term is called compressibility. So this is the slope of the equation of state. Then QSAT, ZSAT. So these are higher order terms. And the second line here, this expansion is called the symmetry energy. So you saw here that this binding energy, if you take the limit very large A and Z and you divide B by A, you will see that all these terms drop out, and what you are left with is one term, which is the volume term, and the other term, which is the symmetry energy term, times delta square. And delta is nothing but the difference between neutron and proton numbers. So that's why we are expanding the binding energy in terms of these two quantities. So one is the density. I mean, this is dimensionless, and the other one is dimensionless, again, asymmetry. And this asymmetry term, so it is written in such a way that it becomes 0 when you have same number of neutron protons, and it becomes 1 when you have pure neutron matter. So you don't have any protons at all. So delta varies between 0 and 1. So now these are the things that experiments tell us, right? So experiments tell us what are these quantities. So saturation energy, the slope of saturation energy, which is called compressibility, and so on. And again, so these, you can see at the bottom, I have written the experimental values. So these are the state-of-the-art experimental values. And these are like, say, 0.15 to 0.16 for me to the -3, energy per particle at saturation. So these saturation properties are what? So on the left cartoon, you see that this is the nature nature of nuclear interaction. So nuclear interaction is actually at saturation, so at a certain density called saturation density, this is the minimum of the energy per particle, and this minimum is called the saturation energy. So this comes from the behavior of the binding energy of nuclei. So from the studies of nuclei, we have all these experimental data. The other thing, like that I said, okay, this symmetry energy and symmetry terms. So this again, this comes from some other experiments, and these experiments also, I gave the values here at the bottom. You see the symmetry energy, and the second term is LSIM, also called slope of the symmetry energy, and so on. And these are measured also by some kind of other experiments. So what experiments? So like one is called giant dipole resonance. So these are resonances of nuclei. Then there are electric dipole polarizability, neutron skin thickness. So what is neutron skin thickness? This is nothing but the difference between the neutron layer and the proton. So neutron radius and proton radius. So this is called the neutron skin. So measurements of neutron skin are now being performed at experiments like P-REX, C-REX at Jefferson Lab. And also, like all these heavy ion collision experiments also tell us about these giant resonances. So all these nuclear experiments give us information about all these quantities that I talked about. So these are the different properties that we when we have a phenomenological model, for example. So we fit our parameters so that they reproduce these quantities. So say I have some coupling constants in my model, and then I tune them so that they are exactly reproducing these quantities. So this goes for the nucleon-nucleon interaction. Now, I also told you that there are these other experiments called heavy ion collision experiments. And heavy ion collision experiments are, they give us information about intermediate temperature, intermediate density, hot and dense matter. So what happens here, I already told you. So there are these heavy ion beams which are made to collide. So these scattered, all these particles you see in the picture at the bottom, they scatter out all these particles. So there is a quark gluon plasma formed, and then this slowly hadronizes, it cools down and generates these strange particles that are seen only in heavy ion collision experiments. And this is interesting for us because this is happening only because there is this hot dense matter being produced in nature. Otherwise you cannot find them at all. So now we can take this information and try to see how to model the neutron star interior. And so what do we expect inside heavy ion collisions? So this comes from particle physics, in the sense that particle physics, the standard model in particle physics tells us that when you break down matter and atoms, you go, if you had a very strong microscope, you're looking deeper and deeper into matter, then you have these atoms. Inside atoms, what do you have? You have nuclei, a dense nuclei, and electrons going around it. Now you look further into the nucleus, there are protons and neutrons. Now even protons and neutrons are composed of these sub-nuclear particles called quarks. And these are, so you see here on the right, protons are made up of up and down quarks. There are 6 different types of quarks, and out of these, the lightest ones are up and down, and protons and neutrons are formed out of them. So this is all we find in nature, because the particles in nature are not dense enough, so they can only be composed of up and down quarks. But what happens in heavy ion collision is that the energies are so high in this hot and dense matter, they can start to populate these higher quarks. So now these new particles are formed. So like lambda particle is made up of up and down, and the next heavy quark, the strange quark. Then you have kaons. These are bosons made up of down and anti-strange quarks. So there are all this zoo of particles which are formed of heavy quarks and can be seen only when there are these heavy ion collision experiments. If you go into the news, so if you look at the page of the CERN experiment, the CERN lab, you will see all the time there are these news about a new particle being discovered. you also must have heard about the Higgs boson, right? So this new particles being discovered, and these new particles are nothing but these heavier and heavier quarks, and these compose these very strange particles. They are also, so S is the strange quark, so these are also called strange baryons or hyperons, and so hyperons and kaons, so these are produced only inside these heavy ion collision experiment. Nowhere else on Earth can you find this. And so these hypernuclei, so hypernuclei are nothing but just like nuclei, but now you change some proton and neutron by these heavy particles. So you can imagine now there is an entire universe there which are almost like normal matter, but then now these are replaced by these heavier particles. So these are only seen inside the collision experiments. Also, the other thing is that, like I said here, you can also form a quark gluon plasma. What is this? So when you have very, very high density, so more than 8-10 times that of the nucleus, then it is expected that all these melt into a free quark soup. And so this is what can also happen in heavy ion collision experiments. When these two beams, high energy beams, are bombarded, they form this collision, they form this plasma, this soup of quarks and gluons. So now imagine all this actually tells us what is there inside the neutron star. So isn't it strange? Because this is the only kind of object in nature, in the cosmos, where you can find these kind of strange objects, and which is why we are studying them. So now if you put this information together and make a puzzle, like a puzzle you put together and make a picture of what is there inside the neutron star interior, then you see that, so this is what the picture looks like. So outside, I told you that there are these nuclei, like iron kind of nuclei, embedded in a sea of electrons. Then as you go inward, you can also see this inset on the right. So this is the crust. You see this outer crust is made up of these nuclei. Then as you are going more and more towards the interior, the density is increasing. The nuclei start to become more and more neutron rich. And at a certain point, it's also called the neutron drip density. So there are so many neutrons that there are also neutrons outside the nuclei now. So this part is called the inner crust. So you see here, the inner crust is now not only nuclear clusters, but also neutrons and electrons. Then what happens is amazing. So this, once you go to very high densities, at a certain point, these nuclei start to become deformed, extremely deformed under this pressure, the density, and they form strange structures. They are also funnily called pasta structures because they look like spaghetti and meatballs and lasagna and so on. So these pasta structures finally, because of very high density, melt into a homogeneous core. So the core is now composed of neutron and a small fraction of protons and electrons. So we are just putting together all the information we talked about already. And now the inner core, so this is the most exotic part of the neutron star. So this is why there are question marks here in this figure, because we still don't know what's going on here. So like we said, there are different theories, and these theories tell us that these can have all these things that you see in heavy ion collision experiment. It can have hyperons, it can have quarks, it can have kaons, it can have all these strange particles which are only momentarily seen inside heavy ion collision experiments. So, I can tell you any story, right? Could you believe in it? So you will say, how can I measure? How can I see it? How can I actually see it from the observations? So that is the point, right? There must be some clue of this interior composition in the observations. So this is what we are trying to detect. Now, the interesting question is, we talked about equation of state earlier, remember? So equation of states, in the beginning, we said, okay, there is only a Fermi gas. Then we also added the nucleon-nucleon interaction to it. Now the effect of adding these strange particles is that what happens is the slope of the equation of state changes. So if you had only neutrons and some protons, electrons, you would have a very steep equation of state, also called a stiff one. And then now you start to add these strange particles. So these strange particles take away some energy, some new degrees of freedom, take away some energy from the system. And this causes a softening of the equation of state, a lowering of the slope. Now you solve the same equation, the hydrostatic equilibrium equations we talked about, remember, the TOV equations, and then you get the mass radius curve for the corresponding equations of state. What you find now is that this stiff equation of state means that if there were only neutrons, protons, electrons, they would have a very high maximum mass. Whereas if you have hyperons inside, they would actually have a lower maximum mass. So this means that now I can go and measure, like observe the masses, and this I already told you in the last lecture how this is done. So from these mass observations, now we can tell these equations of state apart, whether or not they have hyperons. So this is exactly what I also worked on. So these are this is work that was done by me back in 2010. So the point is this. So there were these very high mass observations of close to 2 solar mass which were discovered then. So now the question was, if you have hyperons, then of course it should be that all the equations of state which fall below this line, these observations of 2 solar mass, they should all be ruled out, right? So all this zoo of models that you see is nothing but these different nucleon-nucleon interactions. Some of these are also called strange stars. So these green lines, SQM, that you see on the left, these are pure quark star. On the other hand, these right-hand snake-like structures, so these are all typical mass radius curves, but they have different composition and different kind of nuclear interactions. Now, different people prefer different equations of state, but now whether or not they are actually physical, this constraint can come from observations. So now you impose observations. You see these pulsar observations, yellow, blue, and green lines superimposed on this figure. So we see that any theoretical equation of theoretical mass which is above these maximum mass are the ones. So these ones above, these are the masses, these are the equations of state which are now allowed. The others are ruled out. So this is the way in which we can tell whether or not hyperons can be there, or what we understand about hyperons. So actually in my research, I showed that this is not exactly ruling out hyperons. So because this was called a hyperon puzzle back then, that hyperons should be completely ruled out. They are not there in neutron stars. But then I showed that actually, if you can have a strong hyperon-hyperon interaction, then this is still possible, and therefore this kind of observation actually puts a constraint on the interactions between hyperons, the repulsion between them, and this is something that has to be verified from experiments. Other effects of hyperons, so we already talked about cooling yesterday. So you know that from the flux you can determine temperature, and then from the age you can determine how. So these boxes are these different neutron star temperature measurements. And so these are the cooling curves. So if there were only neutrons and protons, then they would participate in a certain kind of reactions which take away electrons from the system and cool the star. But then if you have hyperons will introduce some new kind of processes, and this would also result in a rapid cooling of the star. So depending on, so not only hyperons, there can also be kaons, there can be quarks, and these again can be superfluid, like I said. So again, depending on what are the subatomic particles which are there in the composition, there would be different. So you see all these dashed lines, so they correspond to different kinds of cooling mechanisms inside the neutron star and for different composition. And then from observing the temperature and temperature evolution, you can say which kind of particles there are inside the star. Someone raised the hand. Maybe I can take this question. Can you unmute yourself? Can you unmute yourself?
Yes, ma'am.
Yeah.
Ma'am, in the last slide where you showed the mask.
Right. Yeah.
Ma'am, I couldn't understand why the those lines which are above that that mark are the possible ones.
Right. So this is nothing but, I mean, so these curves, so these each line is actually a sequence of different masses corresponding to different central densities. Now, for any particular, so these are, like I said, these correspond to different equations of state. Now, a theoretical maximum mass, so each curve corresponds to a different theoretical model, and for each theoretical model, there is this maximum mass. So the maximum mass, if for example, you see a lower curve, this magenta curve, for example, MS1. So the maximum mass of this sequence, which is possible, is lower than 2 solar mass. Then tell me, how do you expect that when you see a 2 solar mass, how can you explain it? You can't, right? So your model should at least be able to explain the observed mass. So this is something that, I mean, if your model does not even have this mass in the maximum, that means it is ruled out. I hope that is clear. There is another question. Neil, please unmute yourself. Okay, it's gone. All right, then. Yes, Tanma.
Ma'am, hyperons, kaons, these are actually, their proper lifetime is very small in our center of mass frame or whatever we are doing in collision experiments.
What
so,
is?
Yeah, yes, ma'am.
Can you repeat what is small? I couldn't follow.
Their proper time means their rest time actually.
Yeah, so they are momentarily produced. So for very small fractions of a second.
Yes, yes, ma'am. So can there be stable equilibrium in interior of neutron star?
Yeah, good question. So this is only possible because neutron stars have such high density. They have extreme densities. So, and also the other point is that, like I told you when we were talking about chemical equilibrium between neutrons, protons, remember that we said that if there are, so this happens when, say, a particle is trying to decay, and then it has to decay to some lower energy level. So if these energy levels are available, only then it can decay. On the other hand, if these energy levels are already filled up, and this is the case for dense matter, so in that case, this reaction is not possible and the reverse reaction starts to happen. So this gives an equilibrium in the system, and this means that these strange particles or even neutron, proton, electron, like I said, in general, neutrons would decay, but then in this system, these are, again, there is an equilibrium between neutron, protons and electrons, and similarly also between, so hyperons, kaons, these are stable components of matter. Strangeness, otherwise on Earth, for example, this is not a stable, we don't see stable hyperons even in heavy ion collisions, only possible in dense matter, such high densities.
Okay, ma'am. Thank you.
There is one more question. Okay. Ayush.
Hello.
Yeah, hi.
Good morning. Ma'am, from the previous question, it is my continuous question.
Can you speak up, please?
Hello, is it audible?
Yeah.
I was saying from the previous question, as you said that the dense massive particles, they are present in equilibrium at the core of the neutron stars, right? So how do we observe these kind of radiations when they fall upon the Earth? Since the Earth atmosphere will block all these kind of radiations, and we can only observe at the space, the telescopes and the observatories that are present outside the Earth atmosphere, they can only detect such kind of minute radiations. But still, these kinds of strange particles cannot be detected since they are not in equilibrium or there is not much density above Earth atmosphere. So how can we detect them?
There is no radiation from these particles. There is no radiation. So these are really inside the core, and this is why we are discussing this here. So it's very difficult to detect them. I mean, there is no way that you can directly look and say, okay, these particles are emitting radiation. It's not so simple. So this is why we are finding these indirect methods to understand how this would affect some. So the effect on equation of state and the effect of equation of state on some quantity like radius, like mass. So this is like a indirect method, because directly I talked about gravitational waves, remember? So gravitational waves is the only thing that brings information from the interior. Everything else, we just see radiation from the surface, and from this we deduce mass, radius, and so on. So we are only observing indirect things, and from these indirect things, that is why this is so challenging to be able to model the interior in such a way that you can actually find some signature in some observed quantity, because we cannot observe them directly.
So when we do these things, in the observatories of CERN, so we try to predict and find out the new particles. So is it that kind of a structure we try to create, that kind of reactions we try to create, so that we could find those kind of minute particles?
In CERN, it's a different thing, because the problem with neutron stars is that they are very far away. We cannot go there and look inside and measure something. In CERN, it's a different thing. They have detectors, and they have, from the tracks of these particles, they can tell like what is the charge and mass of these particles, and they can say, okay, so this particle corresponds to this. Okay, so it's a different thing. They can actually measure what is going on. For us, we cannot measure, so we have to relate to some observable.
Okay, and these minute particles are affected by the strong magnetic waves inside the core as well, right?
Yes, they can affect. For example, magnetars that I talked about, magnetars have very high magnetic fields. Of course, any charged particle, if these are charged, like some of the particles, lambda is not charged, but there are sigma hyperons which are charged. So these will be affected by the magnetic field.
Okay, thank you.
Okay, maybe I should continue and take the questions in the end, okay? Because I have a few more slides to go. Okay, so, all right, I'll come back to your questions. So, so we were talking about, so we were talking about these signatures of interior composition, right? So hyperons have, so I already told you that they have effect on the mass, they have effect also on the radius, they have effect on cooling. What else? So remember, I was talking about gravitational wave emission from neutron stars. Of course, again, neutron stars have many different sources of gravitation. Remember, I talked about glitches, I talked about magnetar flares and so on. So also the other neutron star gravitational wave source I talked about were these oscillation modes in neutron stars. There are different kind of oscillation modes. So even, for example, when two neutron stars merge, this end product that is produced, so this is a wobbling neutron star, wobbling, ringing neutron star, which is like having all kinds of perturbations and oscillations inside. So one such oscillation is called an R mode. R mode is nothing but a rotational mode. It is only there in rotating stars, rapidly rotating stars. And again, this is a complicated physics, but the main point is that if hyperons are present, how would it affect R modes? So if there were no hyperons, so what happens is that these unstable modes, so whether or not these oscillation modes are unstable depends on what kind of composition you have in the interior, because this composition gives it a kind of viscosity which balances out the unstable gravitational wave emission. So this is like a tug of war between viscosity and gravitational wave emission. And when these two are balanced, this is called the critical condition. So critical frequency of R modes can be calculated, which means that if frequencies are higher than this critical frequency, then there will be emission of gravitational waves. If it is lower, then it won't. You see in this figure, this is a plot of this critical frequency as a function of temperature. And this has this V-shaped, a cusp-shaped structure. So anything inside this, all values inside this are unstable. It's called an instability window. And this instability window is determined by the balance of viscosity and gravitational wave emission. And this window is also determined by what kind of particles you have in the interior. If you have hyperons, this will actually change. This will shift, or this will reduce the window, which means that that will also change the corresponding emission of gravitational waves. So actually recently there was a discovery from LIGO. They were tracking one such neutron star, which they know, okay, this is very rapidly rotating. Most likely it is a candidate that emits R modes. So what they did was they tried to observe gravitational waves from this, and to determine, okay, what kind of equation of state is there. I mean, that can explain this kind of observation. So this is something which is going on. There are also many other kinds of effects. So we talked about core collapse and black hole formation during the supernova. This can also be affected by hyperons, whether or not there are hyperons inside. The other thing, stability of the merger remnant. So these merger of neutron stars, I said that it produces a remnant before it goes into a black hole. Whether or not this merger remnant is going to be stable also depends on what particles are there inside. If there are hyperons, maybe they soften the equation of state a lot. There is not much pressure support and it quickly collapses into a black hole. And if there are no hyperons, maybe it's much more stable and stays longer. And we can observe this remnant. And so on the right hand side, you also see simulations of these kind of studies that are going on. So this is like I told you, since we cannot go directly to the neutron star measure, look inside and see, okay, what particles there are. So there is this very complicated method of modeling the equation of state, trying to connect it with some observable quantities, which I talked about in the previous lecture, and then trying to find these signatures. So this is actually what we are all doing right now with multi-messenger astronomy. So the last thing I will talk about, this also, I just added a few slides. This is a very brief discussion. This is, of course, a very complicated subject, but I will still mention it here. So superfluidity, this is something also which is very successful in laboratory experiments. There are widespread applications of superfluidity. And so this was first observed in helium. And then there are many different studies. So for example, we know that if superfluid is put into rotation, then this will produce these kind of vortices. And so this, on the right hand side, you see this experiment of material science where the vortices are pinning to the superconducting thin films. So laboratory studies of superfluids gives us all this kind of information as to what happens when you have this cold superfluid matter which is set into rotation and how it interacts with the surroundings. So in the same way, the neutron star interior can also have superfluids. And so I will come to that in the next slide, or maybe I can go to the next slide first. So in fermionic systems, it is known that superfluidity and superconductivity, so superfluidity is for neutral particles, superconductivity is for charged particles. So this can occur when there is a pairing of these neutral or charged fermions. So these pairs are called Cooper pairs. So this was given by Cooper's theorem, and which says that if there is some kind of interaction, attractive interaction between particles, so they pair up to form Cooper pairs. And then these Cooper pairs, so there is a theory called Bcs theory, according to Bardeen, Cooper, and Schrieffer, back from 1957. And these said that these Cooper pairs, they can actually change the energy spectrum, energy dispersion relation, and produce, below a certain temperature, they can produce superconductivity. So for neutron stars, this was calculated and it was found that this temperature is around 10 to the 8, 10 to the 10 Kelvin, which is great because actually neutron stars, when they are formed, they are hot, or even binary neutron star mergers, these are hot remnants. But once they cool down, when the temperature drops below like 10 to the 9 Kelvin or so, then you expect to have these superfluids. So in the inner crust, you can have neutron pairs. Outer core, you can also have neutron pairs, but in a different kind of interaction. You can have proton pairs, and inside the core, you can even have quark superconductors. So just to give you a picture, you see here this cartoon. So this blue layer is the crust, and in the crust you have this neutron superfluid and these vortex lines and pinning to nuclei in the lattice. On the other hand, inside the, this is the outer core, you see here you can have neutron superfluid, proton superconductor, neutron vortex lines, and magnetic flux tubes. So when you have charged superconductors set into rotation, you have flux tubes. So there is all this complex physics again from superfluidity, and this is also something we learned about from laboratory experiments, right? And now, how do we again measure it from observations? There is a whole lot of modeling that is going on here. And finally, I mean, I will just show you what I talked about yesterday as well. So from glitches, from measurement of glitches, we think that whenever this spinning of the vortex lines to the crust, so there are these vortex lines because this superfluid core has been set into rotation, these vortex lines and flux tubes are formed, these spin to the crust, and whenever there is a sudden kind of change in angular momentum because of rotation, a transfer happens of angular momentum, suddenly changing the rotation frequency of the star and resulting in a glitch. Superfluids can also, I just mentioned this yesterday, they can also change the thermal evolution of neutron stars. So recently, the Cassiopeia A neutron star, Cassiopeia A, so the neutron star was observed and it was found. So you see these red data lines, you see that they were found to be, this cooling, this special kind of sudden drop in the temperature, the cooling was also found to be compatible with a model which can be explained by a superfluid transition. So all these things, so the main story here is that you see, I mean, of course, you know, you can understand that these are so many different fields. It's like neutron star physics is a multidisciplinary field. And you see here, you have experiments telling you a lot of things, theory and observations hand in hand, and you need constraints from all of them. And also you see here, there is an overlap of nuclear physics, particle physics, astrophysics, and many body systems. So all these put together gives you the complexity and the beauty of neutron stars. Finally, okay, there are a lot of things going on which can give us more information. So all these nuclear-nucleon interactions, hyperon-hyperon interactions, there are many experiments going on around the world. So this is the HYPE network, which is shown here. All these different experiments at Jefferson Lab, RIC, FAIR, Daphne, GSI, G-Park, and so on. So all these are conducting these kind of heavy ion experiments, which give us information about the different interactions in strong matter, in dense matter. There are also future heavy ion collision experiments which have started construction. So the CBM experiment, this is a compressed baryonic matter experiment. So this will actually probe heavy ion physics, which is at higher than 3 times saturation density. So we are going from not only up to 2 to 3. In general, heavy ion collision experiments that we were talking about, they probe matter between 2 and 3 times saturation density, and this is going even higher. So we have these new generation of experiments, and of course superfluidity, there are a lot of experiments which are giving us information. So you see that experiments, theory, as well as observations, these like multi-messenger observations, these give us a lot of rich physics of extreme matter that you can learn from this densest form of matter in the universe in the form of neutron stars. So I will stop here. So these are some reference books. I will share the slides on the workspace. So some reference books where you can find much more information about this. So, okay, so I will stop here and you can ask me questions about today's lecture, also about yesterday's lecture if you like. Or like I said, if you could not ask questions during the talk, you have been circulated this Google form, right? So if you write the questions, I will put up the answers in the workspace. So, okay, let's see how many questions we can answer. So, Ayush, did you already ask a question, or is your hand up again for a question? Who else is there? Neil, Sandesh, one of you, do you want to unmute? Please unmute yourself. Neil, maybe.
Hello.
Yeah, hello.
So my question is related to the causality limit.
Sorry, the causality limit on
Yes.
mass radius.
Yes.
Let me see, where is the figure? Okay, yeah. This figure, are you talking about this figure?
Yes.
Okay. Yes.
I would like to ask that why is this limit not same as that of the black holes?
So the black hole limit comes from the calculation of the metric, right? And the causality is just from the speed of sound. So the limit set by speed of sound, that's it. So in any of these equations of state also you can compute the speed of sound, and this is just that limit. On the other hand, black holes, this is, I mean, close to, yeah, I mean, this is higher, 2.5 to 3 solar mass. And this comes from the, in fact, I don't even know if this because there is now this debate on really like distinguishing between a lot of candidates, gravitational wave candidates, which are neutron star, black hole candidates. So we don't know which I mean, whether the neutron star companion in the binary is a black hole or a neutron star. So I don't know if this limit is very stringent. I will have to check this again. But I think this comes from the metric property. That's all, from the metric of black holes.
Like the same question, like if we have a higher radius object, we are allowed to have a neutron star in the mass gap.
If you have a higher radius object, so you can see here there is a vast range of radii. Although right now many of these radii are also ruled out because of several constraints. So I did not talk about it here today. Lot of radius constraints are coming from tidal deformability. Like yesterday, I showed you that the tidal deformability of neutron stars in the merger, they while they deform each other, it depends on the radius. So from the observation of this first merger remnant GW170817, there are strict constraints on the radius as well, and there are other arguments also. And finally, the radius. I mean, this is an older plot, so this. Such a high radius is for large range of radii is not allowed anymore for neutron stars. So is that your question? What was your question about the radii?
Yeah, so I was asking that does that allow neutron stars to exist like some models in the mass gap area?
What allows neutron stars to exist?
Like some of these models do have a possibility of having a neutron star in the mass gap region, provided the radius
mass
is
gap
large.
region. I see. Yeah. So this is I did not talk about the mass gap here. I think I show it yesterday? No, I don't think so. So yes, so there when you have this right now, this question has come up, right? So in this mass gap that we were discussing between neutron stars and black holes, so earlier we thought that there is a mass gap, a difference between the maximum mass of neutron stars and minimum mass of black holes. But actually this limit is now getting blurred because of more and more observations of masses in this intermediate band from LIGO observations. And now, yes, the question of course comes up, because when you detect an object which is exactly in between the masses expected for neutron star and black hole, so of course the question comes whether this is allowed from these two theories. And neutron stars, again, the only neutron stars which will be able to explain very massive neutron stars which are in the mass gap, close to the mass gap, they will be only purely neutrons. Because, I mean, you cannot, I mean, there is, like I said, so in the picture at the top, you see that, so I'd already told you that hyperons, if you want hyperons to exist in two solar mass neutron stars, for example, there is already, you need a very strong hyperon-hyperon repulsion. But then, again, I mean, you have limits as to how strong the 3 nucleon forces are, or hyperon-hyperon repulsion is. So if it actually, like, if it is an extremely high mass neutron star, then probably there will also, it will not be able to explain even such high repulsion or such, so hyperon repulsion or 3 body forces in neutron stars. So in that case, probably it's going to be only purely nucleonic star. So neutron, protons, and electrons. But again, like we said, so there is also causality limit and so on of the model, and then you have to keep it in mind that you should be able to, like your nucleon interaction should be able to sustain such a high stable maximum mass. So this is really like reaching the limit of nuclear physics, the most extreme cases, the stiffest equations of state. All the others will be, of course, ruled out. So this is like why there is so much discussion about what are these objects in the mass cap, because this can put a very stringent constraint on these models. Okay. Anyone else? There was a question from Deepa. Deepa, can you unmute? Yeah. I can't hear you though. I am not able to hear you. Let me check the chats. Okay, in the meantime, maybe Deepa can try to connect audio again. Let me see what questions there are in the chat. So, what is the ultra-relativistic state? So, ultra-relativistic state is the state, like I said, so ultra-relativistic state is when the momentum of the particles is much larger than its the rest mass of the particle. So this limit is called the ultra-relativistic limit. Neutron stars are hot, then why the graph is in the negative direction? So which graph are you talking about? The cooling curve, is it? Or this one? Orgu asked this question. Can you see which graph you are talking about? I'm not sure which graph is in the negative direction. In the inner core of neutron stars, there are quark droplets. As far as I know, quarks can't be found independently. Yes, again, like I said, so this is only possible because of the very high density matter. So in heavy ion collision experiments also, heavy ion collision, quark gluon plasma is found because it is in this hot, like heavy ions, very accelerated particles are made to collide against each other, producing this hot plasma. So in the same way, this is only possible in the high density matter, which is found in neutron stars. Otherwise, in nature, it cannot be found. In particular, if you see this figure, the QCD phase diagram, you can see that quarks and gluons are actually present only here in this part of the phase diagram, and there is a kind of transition called deconfinement transition, and beyond that these are found, and this transition is found at high densities and high temperatures. So this is only possible, in neutron stars, of course. In neutron stars, they can also go to lower temperature, but it has to be density for sure. There is a question from Vinuta about the causality limit. Yeah, so I think we already talked about it. Causality limit is the limit where the speed of sound has to be less than the speed of light. Hyperon-Urca process. So let's see. The Hyperon-Urca process is related to the cooling. So here, so an Urca process, so remember I said that neutrons can decay into protons, electrons, and antineutrinos, and this other reaction, the reverse reaction, is called electron capture. So these two together are called direct Urca process, okay? And there is also similarly a modified Urca process where you have a bystander nucleon for momentum conservation. So these processes, Urca processes, are so nucleonic Urca processes are considered to be the main responsible process which produces neutrinos, and these take away energy from the system, cooling the star. So in cooling neutron stars, these are the most common ones which are considered. You can see here in the figure, direct Urca, modified Urca, these are marked. Now, hyperon Urca is similar. So instead of neutron going to proton, you have hyperon going to another baryon, and there are, so L is a lepton, which means it can be an electron, it can be a muon. So it is similar to the neutron decay, but instead of neutron, it is a hyperon. Other questions? In neutron star, it is not necessarily low temperature, so is high pressure form superfluid? No, neutron stars are low temperature. So again, neutron stars are considered low temperature because the temperature of a neutron star is much less. So temperature, you saw that it is around 10 to the 8, 10 to the 10 Kelvin, around 1 MeV. On the other hand, the energies of the particles in the interior are much higher. And so several 100,000 MeV. Okay, so in that case, the temperature is much lower and it is considered to be zero temperature. So already around 10 to the 9 Kelvin, when the temperature drops below that, superfluidity starts to appear. So I think I answered this today. Are white dwarf, neutron star, black hole the only end states of stars? So far as we know, yes. We don't know of any other forms of compact stars yet. I mean, in the sense, of course, there are some varieties, like I said, neutron stars. Again, here I talked about, when I showed the mass radius curve, remember I said there are these strange stars. There are these strange stars, and strange stars are stars which are composed entirely of strange matter. So there is no like neutron proton in there. So it's a completely strange matter, strange quark matter, just a quark star. So these are also possible. But then these are also counted inside the generic family of neutron stars. Okay, but yeah, I mean, there are some variations of it, but in general, the stability and the kind of particles you have in the interior. So there are, depending on whether these are electrons and neutron hyperon, I mean, in the case, I forgot to say this. So when you have neutrons and then you have some either hyperons in the center or quarks, these are also called hybrid stars. So hybrid star, neutron star, quark star, these are considered to be like one family. And then you have the black holes. So these are three classes depending on the three ranges of the progenitor star masses. Okay, I think there are no more questions. And there is, okay, new question. Explain the phase transition beyond which independent quarks are possible. So yes, so this was the deconfinement phase transition that I talked about. Again, this is a complicated thing to explain, but then again, I just show you the transition. So there are different kinds of phase transitions that are possible in neutron stars. Out of these, there is one called deconfinement transition. There is one called chiral transition. But more or less beyond these kind of transitions, you can find quarks. And in neutron stars, as you can see, neutron stars start from these nuclei and then go to higher density. and at a certain point they go beyond this transition line. So this happens at very high density. So in general, neutron stars can have neutron, proton, electron, which is the outer core. Then it can have hyperons. Hyperons are seen already around 2 to 3 times saturation density. And then when you go to really like 5 times, 7 times, 10 times clear saturation density, that is when you can expect to have quark matter inside, and even like superconducting quark matter inside. Okay. Yesterday you showed us process of transformation of stars to white dwarfs, black holes, if last stage of white dwarfs and neutron stars is black holes. Last stage of white dwarf and neutron star is actually not a black hole. I mean, again, depends on the interaction, right? So these are extremely interacting systems. Like I said, white dwarfs, neutron stars can also be in binary. They can be in binary with a companion star. They can accrete matter. Then it can have another supernova explosion. It can go into a black hole. Again, I showed you this merger of 2 neutron stars. The merger remnant can be a long-lived neutron star, or it can collapse into a black hole. So there are all these possibilities. But then in general, remember yesterday I showed you, maybe I can show you this slide. I don't know if I can share this. Okay. Let me share. Yeah, okay. Oh, I could share, sorry. So in yesterday's slide, remember I showed the pulsar diagram. So here you see that there are these, there is a death line. So the death line is beyond a certain magnetic field. So magnetic field in neutron star starts to decay, and then at a certain point beyond this, when the magnetic field is too low, then the pulsar mechanism will stop, and there will be no pulsations. So that in that case also it is said that like beyond the death line, the neutron star is not anymore observable as a pulsar. But then now you know already that these are all interacting systems, accreting systems, and they are going through different evolutionary phases. So of course they can go into become a black hole as well. Where was my second talk? I think this one. Oh no, sorry. Okay, I think I have to stop here, right? I think I will stop here. If you have more questions, you can, yeah, okay, I will stop here. So if you have more questions, feel free to fill out the Google form and I will answer them in the workspace. So thank you very much for attending this session. Bye. Goodbye.